Okay, let's dive right in. We're going to talk about one of the most foundational ideas in all of computer science, sorting algorithms. This is kind of the hidden magic that makes our entire digital world work, and we're going to start by breaking down the simplest, most intuitive ways to get it done.
I mean, seriously, have you ever thought about that? Every single second, there are just countless bits of jumbled, chaotic information flying around. You go to search for a product, you check a leaderboard in a game, you look through your own files. How does all of that stuff appear so neat and organized almost instantly?
Well, the answer is sorting. It is the unsung hero that takes all that digital chaos and wrangles it into perfect, usable order. Without it, our apps would just feel broken, and finding anything would be an absolute nightmare. So here's our game plan for this explainer. First, we'll talk about why you should even care about sorting in the first place. Then we'll look at the two big families of sorting algorithms. After that, we're going to get our hands dirty with three classic simple sorts: bubble, selection, and insertion. And finally, we'll wrap it all up with the single most important lesson they all teach us.
All right, first up, why does any of this matter? Well, to put it simply, sorting is what makes data useful. It's that crucial first step you have to take before you can search, analyze, or present information in any meaningful way.
And you see the results of sorting literally everywhere. When you're on an online store and you sort the products by price, that's a sorting algorithm. When you look at a gaming leaderboard, sorting. Even something as simple as organizing the files on your computer relies on these exact principles. It's the engine running in the background that stops searches from being painfully slow and helps us make sense of enormous amounts of data. Now, when it comes to sorting, there are really two major paths you can take. There's the simple, straightforward path, the one that's really easy to wrap your head around. And then there's the complex, super efficient path, which is what actually powers all the real-world applications we use every day. The simple sorts, which are our focus today, kind of use a brute force approach. Imagine having to compare every single item to every other item in a list. It's super thorough, but man, is it slow. This slowness scales terribly, which is a concept we call O of n squared, and we'll unpack that in a bit. On the other hand, the fast sorts use this really clever divide and conquer strategy, which makes them way, way more efficient. We're sticking with the simple sorts today because they are, without a doubt, the best way to learn the core concepts. All right, let's get into our first algorithm, bubble sort. I like to call this one the swapper. It's usually the very first sorting algorithm anybody learns, and for a really good reason. It's just so intuitive. The whole idea is incredibly simple. You just go through the list again and again, and anytime you find two items next to each other that are in the wrong order, you swap them. That's it. With every full pass, the biggest unsorted number bubbles up to its correct position at the end of the list, just like an air bubble rising up through water. So here's the play-by-play. You have an outer loop that just keeps track of how many passes we need to make. The inner loop is where the action is. It compares neighbors one by one and swaps them if they're out of order. After that very first pass, we know for a fact that the single largest item is sitting at the very end, where it belongs. So in the next pass, we can just ignore it, which makes each trip through the list just a little bit shorter. But here is the catch. In the absolute best case scenario, like if the list is already sorted, it's actually pretty quick. But for your average jumbled list or a list that's sorted in reverse, its performance completely falls off a cliff. That O of n we mentioned, it means the work grows exponentially as the list gets bigger. And we're going to see exactly what that looks like in a minute. Okay, next up is selection sort. If bubble sort was the swapper, you could think of this one as the finder. Its strategy is totally different. See, instead of constantly swapping neighbors, selection sort is on a mission. For each position in the list, it scans the entire rest of the list to find the one absolute smallest item. Once it finds it, then it puts it in the correct spot. So the logic goes like this. First, we target the very first position. Then, we search the whole rest of the list for the smallest number and swap it into that first spot. Now, that first spot is locked in. It's sorted, done, we never have to touch it again. Then we move to the second position, search the rest of the list for the next smallest, and swap it in. It's really methodical. One big search and find mission, followed by just a single decisive swap for each pass. And here's a really crucial detail about selection sort's performance. Notice anything? It's O of n squared across the board. Best case, worst case, average case. It makes absolutely no difference. Because it always has to scan that entire unsorted part of the list to find the minimum, it never gets a lucky break, even if the data is already perfectly sorted. Our final simple sort for today is insertion sort, and its nickname is the shifter. This one feels supernatural, a lot like how you would probably organize a hand of playing cards if someone just dealt them to you. With insertion sort, just imagine you have two sections, a sorted section on the left and an unsorted section on the right. You take the very first item from the unsorted pile, and then you find its proper place within the sorted pile, inserting it right where it belongs. You just do this for every single item, and your sorted pile grows one by one. And here's how that shifting part actually works. You pick an item from the unsorted side and hold on to it. Then you look back through the part that's already sorted. If the sorted items are bigger than the one you're holding, you just shift them one spot to the right to open up a space. As soon as you find the right spot, or you hit the very beginning, you just drop your item into that new gap. Now, if we look at its performance, it's pretty similar to bubble sort. It has that great best case of O of n if the list is already sorted, mainly because it barely has to do any shifting. This actually makes it the fastest of these three simple sorts if your data is already almost sorted. But for an average or totally reversed list, yeah, it's still stuck at O(n)². So we've looked at three different strategies: swapping, finding, and shifting. But they all share the exact same fatal flaw that just makes them way too slow for the real world. And here it is, the crucial point that ties this all together. At their heart, they all use two nested loops. You have an outer loop making the passes and an inner loop doing all the comparisons. So for a list with n items, you're essentially doing n things inside of another loop that runs n times. That's n times n, which gives us that really inefficient O of n² performance. And this chart shows you exactly what O of n² means in practice. Look at this. Sorting 100 items might take around 5,000 operations. That's manageable. But if you increase that list to just 10,000 items, not even that big by modern standards, the workload absolutely explodes to 50 million operations. The work doesn't just grow, it skyrockets. This right here is that cliff of inefficiency. So you might be thinking, if they're so slow, why on earth do we even learn them? Well, it's because they are incredible teaching tools. Bubble sort teaches you the fundamental concept of swapping. Selection sort shows you a classic programming pattern of finding a minimum. And insertion sort demonstrates how you can build up a solution piece by piece. They are the perfect building blocks for understanding more complex ideas, but you would just never, ever use them in a real-world application. Which, of course, leaves us with a really fascinating question. We've seen why this simple path is so slow, so how do the fast algorithms, the ones that are actually powering our world, how do they manage to avoid that O of n² cliff? How in the world do they sort millions or even billions of items so incredibly fast? Well, that's a story for another time.